Okay, now the second part. So we move on to number 12. And so for the first part, you're just looking for the angular momentum of the thrown medicine ball. And so you're using the equation L equals RMV. But since R, M, and V are already given as R is R, M is M, and V is V, the answer is just actually L equals RMV. And so for part B, you're looking for the rotational inertia of the system, but you're only using the merry-go-round and the buoy. And so the buoy is point mass, so that's just mr squared. And the mass of the buoy is 5, so it's 5 mr squared. And plus 1/2 10 mr squared, which simplifies to 5 mr squared. So I is just 10 mr squared of the system. And so when we go into C, when we're looking for the angular velocity, you're doing I omega equals, because that's of the system, equals the angular momentum of the thrown medicine ball. And so I omega, and since I is 10 mr squared, you're doing 10 mr squared times omega equals RMV. But one of the r's cancels with the r here, and the m cancels here. So you get 10 omega equals V. But since you're looking for omega, you divide by 10r, and you get omega equals V divided by 10r. Then we move on to part D, which is the energy that the boy expends throwing the medicine ball. And so you just have 1/2 I omega squared plus 1/2 mv squared. And since, once again, you know what I is, it's 10 mr squared, and you know what omega is, which is V over 10r, you're just plugging that in. And since M is M and V is V in the case of the medicine ball, you already have those. So once you plug all this in, this is 5 mr squared, and then parentheses V over 10r quantity squared. So it ends up being V squared over 100 r squared. But the r squared cancels with the 5 mr squared, and the 5 cancels with the 100, getting V squared over 20. So then you end up with mv squared over 20 plus 1/2 mv squared. But you move the 1/2 here into this, you get, or a common denominator, so you have 10 mv squared over 20 plus 1 over 20 mv squared. So your final answer is 11 mv squared. Okay, and then we move into the last part, which is how the following changes affect the answer to C. The angular velocity of the merry-go-round after the medicine ball is thrown. Decreasing omega increasing the mass of the merry-go-round would decrease omega, because then m would be greater. So in the equation there, m would be greater, so the entire thing would be less. And then increasing the mass of the medicine ball, if you look at that equation, the m on the right side, if that was more, then that would increase the overall angular velocity. And that's the same with increasing the velocity of the ball, which is m and v here. Just increasing either of those would increase it here, because if this is greater, then obviously the entire thing is going to be greater. And then the child throws the ball at 30 degrees on the diagram rather than 0 degrees. This decreases omega, because now it's not moving on like a straight line, it's moving up. So only part of the energy is moving straight across, because now it's cosine, and so it does decrease.